Hey everyone, so welcome back to another lecture. Today we are going to learn about trees. This trees is nothing but just an extension of graphs which we already covered in our previous lecture. So as we saw different types of graphs which can be cyclic, acyclic or undirected or directed. Trees have a set of rules which they have to follow to be considered trees. First of all, it has to be connected. Like in graphs, it could be this and then another disjoint set. This could be considered as a graph as a whole, but in trees it has to be strictly connected and it has to be acyclic. So no cycles has to be formed. So no loops and it has to be undirected. Next, if you remember correctly, when we did minimum spanning tree or spanning tree in general, we had a case that if there are n vertices or n nodes, the edges will be n minus 1. The same is this condition for trees. Let's look at an example tree. This is an example tree. Now let's understand few of the terminologies which will be used. The main node from which all the edges are coming from or originating from is called as the root node. These are called as children, which are the extensions of any node, and the originating node is known as parent. The nodes which have no further children are known as leaf nodes, which are the last, and this is in general is the height of the tree, and the depth of any node is just the distance from the root node. So this is the depth, this is the height, and these are the basic terminologies. Next, let's look at an example of a general tree. So in this, we can see that there is no cycle being formed, and it is not di it does not have any directions, and also it is a third condition was it was connected. So this can be qualified as a general tree. Next, this is a binary tree. A binary tree is a tree in which any node can have at max two children. It can be one, but it cannot cross two. So here we can see that it is a perfect binary tree which in which every node has a two children, except like obviously this is a root node, so it does not have any parents. But yeah. Next, this is a BST or a binary search tree. In the binary search tree, the condition is that the left node, this is the root node, and this is the right node. So the left is smaller than the root, which is smaller than the right. So if all the nodes follow this condition, we can consider it as a binary search tree. So as we can see, 5 is smaller than 10, which is smaller than 15. 4 is smaller than 5, which is smaller than 6. 9 is smaller than 15, which is smaller than 20. So this incomplete is a binary search tree. This is very useful and we'll see the applications later. Next, we have the structure, how we represent a tree. A tree is basically just a connection of nodes. So let's define a node. Each node will have some data or a value. So it has a property or attribute for data. Next, another pointer of node data type, which is here, which is just this is a custom structure which will have two children, left and right. Keep in mind this is only for the binary tree because if it is a general tree, it can have many children and not just left and right. So this is for binary tree. And it is not necessary that it will have two children always. It can have one children also. And it is usually then denoted as left and there will be no right. And now the most important part, which is traversals. In any data structure, traversing the data structure is the most important. So we mainly have four types of traversals. First is a pre-order traversal, in which we go from root, then left, then right. So if I have like A, B, C, D, E, and F. So what it says is first I'll visit the root node, which is A. So this is the path of my visiting or traversal. So first I'll visit A, then I'll visit the left node, which is B, and then I'll visit the left again. You do not get confused that then I have to visit C because it is written right. I'll keep visiting left till it is possible. So B ka left is D. Now I cannot move further left because this is the leaf node. It does not have any children. So after D, I'll move on to the right. So I think this is D. Right of B, which is E. Then I'll come back to B. So after B, the right of A, which is C, and इसका left is F. So this is the path for pre-order traversal of this tree. Now let's look at in-order traversal, which is left, then root, then right. This was root, then left, then right. So if I consider the same tree, mhm, 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 and left. So if I consider the same tree, the path would be I'll start from the leftmost leaf, which is D. So I'll visit D. Then I'll visit uska root, which is B. Then I'll visit the right one, which is, sorry, I'll first visit the root because I'll go visit till it is possible. So I'll visit A, then I'll visit E, then I'll visit F, and then C. So this is the path that I'll follow. Next, we have post order, just left, right, and root. So if I have A, B, C, D, E, and F, the path would be B, then E, then B, then F, then C, and then A. In level order, it is the typical breadth first search. So for this only, I'll write it would be A, B, C, D, E, and F. This is a bit confusing. Just keep in mind these things. Sometimes it is confusing and you may get wrong. Next, we have few applications. It is tree system is usually used for managing files or some hierarchy. Like in our file manager also, we implement it by using trees while searching. So for sorting and searching, the best method is trees. We also use it by heaps, and we maintain scheduling in operating systems for priority. We use compression for reducing the size of any files or images or videos by using Huffman codes. Now, this is somewhat an important topic as per college portion also. So I'll be explaining this in detail. So firstly, it is a greedy approach, keep in mind. Next, I'll teach you by example. So for example, this is our message which I want to send. So the number of unique characters is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total I have 13. So what happens is normally you send it by ASCII values. So A is represented by 65 and like that it goes for till Z, and then we have small characters as well. So we represent it by using 8-bit. So if for this I have 13 and sorry, the total length is 20, the unique characters are 13. So if I use 8 bits for each of the character, so I'll have total 160 bits. Now what we can do is we want to reduce this. We want to get it to the most minimum value possible. So there is a method fixed sized code. In this, what we do is we assign our custom codes to the each of the character because uh, some few of the characters are repeating, so I do not have to assign a unique value to them each and every time. So what I can do is I'll just write the frequency. I'll not have duplicate values here, and then I'll assign because I have 13 values, so I'll need 4-bit code because 2, 4, 16. So I can represent 16 characters here at max, and I have 13, so I'll represent it by using this. So here I'll have 4 into 20, which is 80. So here my size is diminished to 80 bits. Now, but I also have to send a chart for each of the character because how will the computer know that this is corresponding to character V? So for that, I'll have to send some extra chart data also, but still when I add it, it will be less than 160. That's for sure. So this is a fixed size code method. Next, we have variable size code, which is Huffman encoding. In this encoding method, this is the same thing. So don't look at this code part now. I'll come back to it later and I'll explain this. Focus on this. So this just I've written all the unique characters and their frequency count. The next step is to build a Huffman tree. So in this count, arrange them in ascending order here, least to highest frequency. So I've arranged all the characters with 1, then 2, then 3. The sum would be 20 because the total number of characters in the message with the Alankar Institute is 20. Now, next, what I have to do is I'll take the two most minimum characters and I'll add them. So I can take one and one. And there are multiple ones, but I'll take any one. So let's start with the leftmost two. So I took them and I added them and forget these zero and ones for now. I'll explain that too. So I'll just add them one and one and it becomes two. So next I'll keep doing this because now just forget this. Now imagine that this one and this one have been used up. So after this being used up, I have two, one, 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 two, three, three, three. So now I'll again do the same thing. I'll take two most minimum. So I again have one and one. So I'll use them up and create a two. Same for this, same for this. So now I have two, 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 and then one, two, three, three, three. So the two most minimum would be 2 and 1 because 2 and 2 is 4, 2 and 1 is 3. And yeah, so I can use this one and this 2 and this one. So I'll take these two, I'll add them up and it becomes 3. So even this is used up now and this is used up. So I have 2, 2, 2, 3, 2, 3, 3, 3. So the next most minimum would be 2 and 2. So I'll add them up and create a 4. After making a 4, the next most least would be 2 and 3. I can take this or this. So I'll take this, for example, and it becomes 5. And next I'll take this, and it becomes 5. Next I have, so 4, 5, 5, 3, 3, 6. So the most minimum would be 3 and 3, which is 6. Now I have 4 and 5, which whose sum is 9. Next I have 9, 5, and 6. So I'll use 5 and 6, 11, and then 9, 11, and it becomes 20. So after we reach our original length, we have to stop. Obviously, we cannot go any further ahead. After using everything, we have to assign 0 to the left edge and 1 to the right edge. So assign 0 to every left edge and 1 to every right edge. So after doing this, if I want to reach, for example, V, my path would be 0, 0, 0, and 0. So my path to V, the code would be 0, 0, 0, 0. My path to D would be 0, 0, 1, sorry, 0, 0, 0, and 1. So my path to D would be 0, 0, 0, 1. I have not written for Y, so let's calculate it for Y. For Y, I have to go from 0, 0, 1, 0. So for Y, it's 0, 0, 1, 0. Likewise, so now let's check for I. I is here, so I go to 1, 0, and 1. So for I, it's 1, 0, 1. Likewise, for N, it's 1, 0, 0. For T, it's 1, 1, 1. Now, a thing to observe right here is the characters with the most frequency or the most count will have a shorter code. You can observe this. I has 3 as frequency, but its code is of 3 bit. Whereas the codes with the least count, like 1, all have 4 bits. So that is the speciality of Huffman encoding. So to reduce the total number of bits used, what we do is we assign a longer bit for the least frequency characters and a shorter bit for the most frequent characters. So after adding this, we'll have an even lesser value than the fixed size code, which is 80 plus x something. Here also the x will be same, but this will be lesser than 80. So that's everything about Huffman encoding. Next, we'll solve some problems on graph and tree. To solve this problem now, which is maximum MST, this is a confusing question and it may have many approaches, but I just solved and tried one approach which I'll be sharing with you. So the question says that there was a weighted undirected complete graph. What is meant by complete graph is that each and every node is connected to each and every other node. So the total, like if you have ever done the handshake lemma, or anything. So the total number of edges would be n into n minus 1 upon t. So for example, if the number of nodes is 5, so this would be the complete graph for it. If it is 4, it would be because each and every node is connected to each and every other node. It says that the weights have been scrambled, and while we recovered the multi set of weights, we do not know which edge had which weight. So in overall, we know that the set of weights which we had, but we do not know which edge had which weight. So there can be any possible assignment. So it says that among all possible assignments of weights, what is the maximum possible value of the MST? So it says that what would be the maximum MST value? And it says this we have our first n input, which is the number of vertices. So if we have the number of vertices, we know the number of edges. And in the next line, it gives us m integer of the weights. And m is obviously this. And we have to output the maximum value. So initially, we have taken t inputs, and I'll explain why I took this gap integer. So after taking n, and this is our result, input n, I'll shift it above, input n, then calculate with the value of m, and inserted this array of m size and then populated that array After doing this, so we have our array, we have taken all the inputs. Now let's try and gather some approach. So let's look at the samples. First is there are two vertices and the edge obviously there will be only one edge. So the MST would be 42 only. So the output is 42. Next we have three vertices of 1, 2, 3. Now I don't know if it is 1, 2, 3 like this or this is 1, 2, 3, but it does not matter because it is just three edges. So I can write anything. Now what it says is I have to give output the maximum MST. So for example, if I start with this edge or sorry, this vertex, I do not know which would be the adjacent edges, the values, but I can randomly select. So imagine this as a game theory. You are playing and your opponent is the computer. So your opponent is trying to defeat you by giving you the maximum value so that you do not achieve your MST. But that is our uh, approach. That is what we need. We need our maximum MST. So we'll use it to our benefit. So what the computer will try to do is, if I select this vertex, the computer will try to maximize my choice by giving me 3 here and 2 here. So if I get 1 here, then I'll obviously choose 1. But it wants me to have the maximum value. So it will offer me two choices, either 3 or 2, and it will give me 1 here. But now it's my turn. So I'll try to defeat the computer. And my goal is to select the MST, which is minimum. So I'll go with 2. So after choosing 2, I only have one option left, which is 1. So my MST would be 2 plus 1, which is 3. That is right here. Next, I have 4, and each and every weight is 5. So it does not matter if I have 4 vertices. My MST will have 3 edges, like this or anything like this. It does not matter. And each of them is 5. So it will be just 3 into 5, which is 15. Now, if now I got the idea of game theory by here. So if I proceed with that ideology, and as it is given that all the weights are scrambled, I do not know which edge contains which weight, or what is the value, or what is the cost. So randomly I'll select any edge. This is for n is equal to 5. So the number of edges would be 5 into 4 by 2, which is 10. This is the complete graph for 5 vertices. So for example, I select this node right here. What the computer will try to do is it will try to force me to opt the maximum value. So it will give me the options of, for example, all the weights are from 1, 2, 3 up to 10 for simplicity. So it will offer me the choices of 10 because I have four options. It will give me 10, 9, 8, and 7. Now you may ask why only 10, 9, 8, and 7? It can be anything. So for example, if it is 5, 4, 7, and 8. So out of 5, 4, 7, and 8, I'll obviously choose 4, which is lesser because now it is trying to force me to take 7 because I won't take 10 or 9 or 8. I'll take 7. But if it gives me a smaller value, I'll obviously choose it. So if I had to play, if I had the option to be the computer, I'll try to defeat myself by giving these four options because this is the best option that I can give. So I'll choose 7 right here because it is my turn now and I want to choose the minimum. So I'll choose 7. Now it is the computer's turn again. What it will try to do is I have three options now. Because I chose 7, I'll go this side. I have three options. This, and this. So I've used up 10, 9, 8, and 7. Now it will offer me the next three biggest choices, which is 6, 5, and 4. Now it is my turn again. Now what I'll do is I'll opt for 4 obviously because I want the minimum value. I'll take this. Now I have two options. And out of these two options, it will try to again force me by choosing the maximum value. So it will take 3 and 2. I will obviously choose 2. And then there is only one option left, so I'll choose 1. So my maximum ST would be 4 plus 3 plus, sorry, 7 plus 4, which was 7, then 4, and then plus 2 plus 1, which is 14. So this is my answer for vertices n is equal to 5. Now let's try for n is equal to 6 once and confirm if the answer is correct. So for 6, we will have 6 into 5 by 2, which is 15, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and the last edge would be this 15. So I'll randomly choose one vertex. If I choose this, it will try. I have five options now. One, two, three, four, and five. So it will force me into choosing the highest five. So 15, 14, 13, 12, and 11. So I'll be forced to choose 11. After I choose 11, I'll have one less option. So I have four options. So it will give me 10, 9, 8, and 7. If I'm correct, yeah. So I'll choose 7. Next, it will give me three options. So it will be 6, 5, and 4. So I'll choose 4. Next, it will give me two options, 3 and 2. So I'll choose 2. Then again, it will give me one option. So this time the answer is 1 plus 2 plus 4 plus 7 plus 11, which is 25. Now, if I apply this logic here, what it will do is 1, 2, 3. If I choose randomly this, it will give me 2 and 3. So 2 plus 1. So 1 plus 2. If I do it here, it will give me, as all the values are same, it will give me 5 plus. So anyways, this is the toughest situation because if all the weights are equal, it would be the easiest. So by observation, what I observe right here is a pattern that if I sort the weights, first, always I have to pick the smallest one. See, this can be another approach would be to start by the smallest one, but I've chosen the game theory for explanation, and that is how I understood it. So it was easy for me. So if I start with the smallest one, this is only by observation. My logic was that I would take the nth largest value. But now for coding it to implement it in code, I have observed that it always contains one. It always starts with one, and then it has two, and then it increases. Like if I have to have only three edges, then I'll go till four. If I have to have four edges, it will go till seven, and then 11. So the pattern here I observe is one. So after one, it adds one. Then after two, it's add twos. Then it adds three. Then it adds four. So imagine this as a index. So if I have, for example, I had four vertices, then how many edges did I have? 4 into 3, 12, 6. So 1, 2, 3, 4, 5, 6. So imagine these as the indexes. For now, don't assume it as zero-based index. Let's use this. So first I'll choose the element at index 1. Then I'll choose the element at index 2, then at 4, and then at 7. But because I had only 4 vertices, I need only 3 edges. And the 3 edges would be at index 1, 2, and 4. And keep in mind that this is after sorting. So sorting is important here. There may be a better option, but this is how I saw it. So to implement this in code, so this till here it was clear that we just took the inputs. Now I want to have a variable gap, and this is my answer. So firstly, I sorted our array. I'll keep this above. After sorting it, I started the for loop. So for int I is equal to 0, j is equal to 0. So I'll explain why I took I and j both here, but keep focus on this. J is equal to 0, j less than n minus 1 and j plus plus. This is our regular expression. So just replace I by j. Now, why I took this I is because I want to keep another variable for focusing on the jumping values, like the answer which I want to include in my the elements which I want to include in my final answer. So if I take I is equal to 0, I is equal to 0 means this, the first element, the very first element I want to include it. So I'll directly add that to my sum, W of I, which is 0. Now next, I already initiated gap with the value of 1. So first I want to increase it by 1, then I want to increase it by 2. So first I increment I by 1, which is gap. Then I increment gap as well because now I want, in the next iteration, I want to increment it by 2. So I've incremented the value of gap as well to 2. Now in the next iteration, what happens is sum is equal to plus is equal to W of 2. After W of 2, now keep in mind the value of gap is also 2. So I plus is equal to gap, I becomes 4. So, or 3 if we use zero-based indexing. And then I again increment the value of gap. And this happens for n minus 1 times because I want n minus 1 edges if I have n vertices. So hopefully you understood the solution. I'll just run and submit it. This is the code I submitted earlier, so it should be successful. And yes. So now my friend Arya Singh is going to explain another problem on code forces.
Yeah. So we'll be doing a very simple problem based on the pre-ordered traversal of trees. The problem states that you are given a rooted tree of 2 to the power n minus 1 vertices. Um, the tree has either 0 children or 2 children, and all leaves of this tree are at the same distance from the root. Hmm. The root has index 1, and each vertex x has a left child 2x and right child index 2x plus 1. Now we know the pre-order traversal of a general tree. What they have specified is that the pre-order string of some vertex x. So if I have a vertex x, I have a pre-order string for that particular vertex. So if that vertex is a leaf, then the pre-order string of x is simply the character sx. Right. And if that is not a leaf, then the pre-order string for that particular vertex is the character present at that particular vertex plus the left and right subtrees. So it's the concatenation operator. Um, Now the problem for us is find the different number of strings that you can obtain given that you can swap two subtrees and maybe you can swap two or more subtrees. Let's take a very, very general example. Given a subtree, uh, let's suppose n is equal to 2. So the number of nodes that I will have will be 2 to the power n minus 1, which is, I think, 3. So I'm having 3 nodes. Um, Something at here, something at here, something at here. Obviously, I need to have 2 children. That is satisfied. Now I will be given a string S. String S contains of only A or B characters. How do I know it? Yeah, the second line consists of only A or B character and nothing else. So let's take A, B, A. So the root of this tree will consist of A. The left child will consist of B, and the right child will consist of A again. Now, what is the pre-order string I will get? The only pre-order string that I can get is A, B, A. Why is it the pre-order? Because I go to the node, I visit the left child, then I visit the right child. Since the left is the leaf and the right is the leaf, I just simply print them. Now, given the condition that I can swap two subtrees, which could be two leaves as well. Interesting. So there comes one more possibility that I could have written this as A, B. What you get? A, B. So the total number of pre-order strings that you can get after doing the operation any number of times. Now, if I swap this again, it will be the same thing, right? So the total number of unique pre-order strings that I can get after performing any number of operations is practically two. That is the answer. Hmm. This was the test case I took, right? Similarly for AAB, because this is the same thing, really. Now you have to predict all the substrings that are possible. One way to solve this is to actually create a tree maybe and go around by swapping the subtrees. The other way to solve this is a very clean trick. Um, if I can show that. The trick is to actually use a DP for this. How will I use a DP for this? What I can do is that I can say the leaf will always be a single character SX. So the number of ways to pre-order traversal this thing and print the pre-order string for this is practically one. Now then I can build upon this. I'm going from bottom to up. This is a bottom up DP, write it somewhere. This is a bottom up DP approach. I can say that the leaf will always have the number of ways of pre-order string as one. And if I am reaching some node X, let it be Y for this time, then if I swap this and if this and left and right subtrees are different, if the left right subtree is not equal to the right subtree, then the number of ways of having the pre-order traversal string will be into two. So if I have something which is like A, A, then there's only one pre-order traversal string. You cannot swap these. There's, I mean, no logic. And similarly, if I have BAA, you cannot swap this. Mm. So you can only swap if these two are different. So if the left subtree and the right subtree are different, then only you can swap, and then only the count will multiply by 2 itself. Yeah, that is practically the logic. Um, we can use two arrays to store all this. And yeah, let's build upon this. Let's see how the code looks like. Uh, and we'll discuss it further here. Let me close this for a moment. And let's actually start coding. So the very first thing to do is that this does not have any test cases. Uh, what I can do is, let's see, have, yeah. So if the given n is 4, then the number of nodes will be 2 to the power 4 minus 1, which is 15. So for each node, I will get a character assigned. So let's quickly do that. Uh, I have the nodes and I have the string s. Couldn't I do? I can use a vector maybe. Kind of vector this should be. Let it be string. And let this be, for some reason, I can call this as canonical form. What is canonical form? Canonical form is basically if I have A, B, and A, B, A, which is the lexicographical smallest string. Yes. I'll call this as the canonical form, right? I don't want to write this much. It's simply second. Uh, so let's define the size here. What is the size of the nodes? It's typically 2 to the power n minus 1. So let me use the left shift operator for this. This is practically 2 to the power n minus 1. No need to discuss this further. And the canonical forms will be the exact number as that. And let me define one more thing. Yeah, I can define it. It's current, and we can call it the number of ways. Same as the number of nodes, and let me initialize each thing with 0. Simple, nothing complicated. Now let's go from the bottom to the up. You can simply write a for loop saying size minus 1. Now what I'm doing is that if this then 3, let this index be 0. Why you should be careful? Because they have said with index will be 1, and left child will be 2x, right child will be 2x plus 1. For simplicity, I'm considering it as 0. Left will be 1, right will be 2. That's how we'll go. And what is your answer? Your answer is basically whatever is there in the base vector, 0th node, because this is my root. And since I'm building from the bottom, I'll have to print the number of ways creating the pre-order string for the 0th node, which is practically the root. Right. So yeah. So for that reason, I'll start with size minus 1 since I'm considering the 0th index. If you are confused, uh, just revisit this thing. We'll go up till 0th node. I'll do I minus minus, and let's see what we can do. The very first thing that I can simply do is that I can write cout ways. See, maybe you guys use endl or slash and the way you like endl more. And there's a very important mentioning that you have to use, let's see, yeah. So I'll change my modulo. This I'll print my answer with respect to this modulo. Uh, and let's see if we can check. So for the logic, let's see. The number of left trees. Instead of the number, I'll just write the index of the left subtree. Could be if I'm on the ith node, the left subtree index would be 2I plus 1. That's clearly right, right? The right subtree index would be 2, right? That's clear. And since you can have either 0 or 2 children, there's no case for 1 children. So to determine if it's a leaf or not, we can simply write if L is greater than equal to size, then that means that is the leaf. I can say the canonical form at the ith index, which is the root of the child, which is not there. So that is the leaf I'm talking about. So it could be simply the single character. For printing a single character, you could have different ways. Using a char is probably appreciated, but I just like to print it this way. Simply, essentially, it means print one character in the string, which is consisting of S of like nothing complicated. And could be the number of ways of creating a pre-ordered traversal string for that particular leaf. Practically one. If that's a leaf, then this is the case. If that is not a leaf, then you can have only two possibilities. Either you switch the left subtree, either you switch it or you don't switch it. If you are switching it and you are having the same thing again, then it's of no use. You will count it only once, else you will count it as two. So what we can do is that we can create two strings. Let's say there's a string P1. Say there's a string P2. I'll create a canonical string, which is um, it's a P, which is minimum of P1. It's significantly minimum. And then the canonical form of this thing that I'm standing will be simply P. And yeah, a number of ways. Let's discuss this. So, simply the string P1, since it's the pre-order traversal, actually it's given also. You first print the character, then you print the left substring, and then the right substring. Obviously, in pre-order traversal, you do that. So, what we can do is that I can write S of I, first character from S of I, so whatever that is, A or T. Then I can go and traverse to the left, then I can traverse to the right. So that could be canonical form of left plus canonical form. That is the only thing that you can obtain. And for the second string, if possible, reverse it. So these are the only two types of periodic traversal you can do, going from bottom till up. Then you compare if T1 is not equal to T2. First, you create the canonical form for the ith thing. Then you say that the number of ways will be the number of ways of traversing the left subtree into the number of ways of traversing the right subtree. And since it could be a very big number, I can maybe write it as modulus for constant. Maybe written as mhm, if yeah, the thing is canonical of left is not equal to canonical. So what I can do is that ways I would be say ways I strong. Again, it's practically this should suffice. If I'm not, what we are doing is that we are just going from bottom till up. We're going from bottom till up, and for every non-leaf node, we are just switching the characters. So it's practically working as a pre-order traversal only, since we are switching the left and right only and just adding the current one to the starting every time. For the leaf, we have one and a single character list. Let's see if there's any mistake I can find right away. Mhm. Let's check it for one test piece. Uh, test case one, we have 16 as the out. So there are possible pre-order strings that you could make. for this type of sequence given 4, I cannot it, but given 4 as the n value, which practically means to the power n minus 1, which is 15 nodes. 15 nodes in this sequence, if you go from bottom till up, do the pre-order traversal for each, uh, except for the leaf, because the leaf has the single character. You can obtain 16 different combinations of those strings. It's very good. It's very good. I can do this simply testing. Um, yeah, so that's, I think, basically it. The question was pretty simple. It does not consist of creating pre-ordered traversal as such. You just need to count the number of ways. And since you know that the number of ways will be obviously the number of ways you can traverse the left and the right, you just multiply it. You keep one thing as the base, which is what canonical data structure does, and you traverse it for the left and right childs. And instead of coming from top to bottom, because obviously if you come from top to bottom, there's no use. You have to find the value for the top one. Plus, if you come from top to bottom, I think you could do it, but yeah, no, you can't count the number of swappings. You need to come from the bottom to because you need to swap subtrees. Maybe you could start uh, from top end. Maybe you could think of that solution as well, but yeah, there could be a different solution to this also. Um, yeah, I mean, from the bottom, maybe we could somehow figure it, give a different label because what ultimately you have is that if it's a 1 1 1 1 1, height will be fixed. Yeah, but no, the characters will be different. Best solution would be to go from the bottom till up, and that's why this thing works. L and R are just the indices, and this is nothing but to the power n minus, which is already given in the question. This is to find the leaf node. This is the canonical structure. This is the number of ways of counting one leaf. We create two p-order traversals, one with the left, one with the right. Swap it. They both are different. Then you just add one to the base. No, actually, multiply into two. Sorry. And then you print the topmost number of ways. That's how the DP will get formed. And obviously, modulus by the constant value which is given. Just the answer could be too large. You can try around, you can go around, create a new solution if you want. Yeah, we can create a lot of solutions with this. I think this is way possible. No. What do you
Um,
think?
that's the solution, I guess. Thank you so much. Hope you join in us in our future lectures as well.